The last section we're going to talk about with Chapter 5 is 5.8, and this is all about characteristic polynomials. Sometimes these are just called characteristic equations, what we're going to be doing with this. Now, earlier in chapter, or section rather, 5.6 with recurrences, we had mentioned that the order of a relation is dependent on how many terms back you have to go. So something is second order if you have to go back 2 terms, in other words, to the k minus 2. If it is to the k minus 5, that would be fifth order. And specifically what we're going to look at here is using the characteristic polynomial to come up with some type of explicit formula for a recurrence relation that may not have an obvious explicit formula. And before we can even do that, we have to identify kind of a special type of recurrence relation. Those are second order linear homogeneous recurrence relations with constant coefficients. Sounds really fancy, but all it means for us is that you have something which is second order. So that means, like in this case, we have b k minus 2 here. So this makes it second order. And b cannot equal 0. So again, we have to emphasize here, this can never equal 0. If the k minus 2 term is equal to 0, then this would actually only be a first order linear homogeneous recurrence relation. All right, now let's take a look down here at a few examples. This first one here, first thing we want to check is, are our coefficients constant? We have a 3, we have a 2, both of them are constant. We have the k minus 1 and the k minus 2. So this one is in fact a second order linear homogeneous recurrence relation with constant coefficients. All right, if we check this next one here, we have k minus 1, k minus 2, k minus 3. That makes this not second order, this would be third order. 0.5, negative 0.785, k minus 1, k minus 2. Although we have these decimals going on, this is still technically constant coefficients, and we have the k minus 2 term, makes this a second order. Now, this last example here, you'll notice this negative 1 as a coefficient is constant, but this one has k minus 1, which is not a constant coefficient, which is why this cannot be a second order relation with constant coefficients. Let's move on here and talk about the characteristic polynomial. If you're given some sequence where, and should mention that we're dealing with a geometric sequence here. We are making an assumption that this is an infinite geometric sequence. We can derive a polynomial equation, which is given down here. So your polynomial equation, a sub k equals a times the k minus first term plus b times the second term. So if you have, in other words, what we defined on our previous example here, if you have one of these second order linear homogeneous recurrence relations with constant coefficients, then you may use our characteristic equation, which is right here. Okay, so you'll notice that this is a quadratic equation. Now, if you're dealing with a quadratic equation, two things can happen. It's going to factor or it won't factor. If it factors, great, makes things super easy for us. If it does not factor, we have our good friend, the quadratic formula, which we can go ahead and use, and we'll see an example of this a little bit later. Consider the sequence c sub k, or I should say the recurrence relation, equals negative 4ck minus 1 minus 4ck minus 2. In this case, a is then equal to negative 4, and b is also equal to negative 4. What is the characteristic equation of this sequence? Go ahead and plug in. We have t squared minus negative 4t minus negative 4 equals 0. If you want to go ahead and clean this up all at once, you can do that. You don't have to write that extra step. So we have t squared plus 4t plus 4 equals 0. Let's see, what are possible sequences this recurrence relation defines? Well, in order to figure that out, we first need to deal with what's going on here. Let's go ahead and factor this out and find the roots of this polynomial. Essentially, the roots of the characteristic polynomial give us possible sequences in other words, possible ways that we can generate the sequence. So if we factor this, we have t plus 2 times t plus 2. So let's see, multiplies to 4, adds to 4, we're good to go. So that means that t has to equal -2. And in this case, then there's only one possible sequence that this will generate, which would be, we had, let's see, we said 1, then that would be to the 0. So we have 1, -2 to the first, -2 to the second, and so on and so forth. So what is this generating? Alternating powers of 2. Now, something that's kind of neat that we can use the characteristic polynomial for, we said, is to come up with some type of um, explicit formula for a recurrence relation we previously could not. Now, let's look at an example, and we're going to use what's called the distinct roots theorem. Now, we're saying if we have this second order linear, you know, the whole thing we've been talking about all along here, that satisfies our characteristic equation if there are two distinct roots. In other words, not like the example we just saw. If we have two distinct roots, then the sequence can be given by some linear combination of the sequences of those roots. So again, you'll notice here we have c times the first sequence plus d times the second. This is what we call, again, a linear combination. If you've taken a linear algebra course, then this is probably not the first time you've seen this. So let's go ahead and dive in. In this example that we have, what are a and b? Well, a is equal to -1, b equals 12. So according to our characteristic polynomial, we have t squared minus -1 is plus 1t minus 12 equals 0. And this factors into t minus 3, t plus 4. Unlike the other example, we have two distinct roots now. So we have t equals 3 or t equals -4. And again, we're going to have some linear combination of these two things. So maybe let's say r sub r to the n is the sequence defined by this one, and s would be the sequence defined by this one. So if you think back to how we set up our linear combination here, let's use what we've just learned to write this out. R sub n is equal to some constant we don't know times 3 to the n plus some other constant we don't know yet times -4 to the n. Now, as is, we don't know what c and d are. However, if we come up with, or if we're given some initial conditions, we can absolutely go ahead and find this out, which we'll look at in our next video.